SitP is a not-for-profit organisation for the promotion of science, teaching and critical thinking. We meet here on the second Wednesday of every month at 7:30 p.m. And each month we have a guest speaker who comes along to do a talk on their subject and follows up with a Q&A. We approach each subject by looking at the available evidence from a scientific, sceptical and rational viewpoint. This month we talk about particle physics, bosons, muons, gluons and God particles. You probably remember the headlines in July 2012 when it was declared that the physicists at CERN had discovered the Higgs boson, the final of the 16 theorised fundamental particles to be discovered. These include electrons, photons, gluons, etc. But until 2012, the Higgs was only theorised. No one had actually produced any physical evidence for it. I've got a vague idea of what photons and electrons do, but that's about the limit of my knowledge. Luckily tonight we've got Professor Jon Butterworth, one of the lead physicists of the ATLAS experiment at CERN, the very experiment which confirmed the existence of the Higgs in 2012. Jon is Vice Dean in Maths and Physical Sciences at UCL. He's a holder of a Wilson Research Merit Award from the Royal Society, member of the editorial advisory panel for the Nature Communications Journal. His early research focused on the Zeus experiment at DC Hamburg, and more recently, as previously stated, he discovered the Higgs boson at CERN, something which tonight will tell us about and is significant. So please welcome Professor Jon Butterworth.
Thanks very much. It's a real pleasure to be here. I thought I'd clean up my biographies on the internet, because the Vice Dean thing finished ages ago. I'm now head of the Department of Physics at UCL. But thank you very much for that introduction. The book view, by the way, is just a point. But I have a book out, which is on the table at the back, which begins with me playing pool with a guy from Channel 4, Tom Clark, in a kebab shop with pool tables, obviously, in Geneva. And that was a very weird experience for a physicist. So it was the day before, it was actually July the 3rd, the day before we announced the discovery of the Higgs boson, and the whole media circus was in town because of it. CERN's picked up, it's quite well known now, even my mum knows the name of my experiment, which is good. Well, I told her often enough, but now she remembers because she's sitting on the news. The whole thing is a bit strange for a science experiment. And part of the reason I'm doing these talks, and part of the reason I wrote the book, is because I think that's great that science is out there. It's great that particle physics is a matter of public interest. But that hasn't been an easy journey for the scientists involved, because a lot of us don't really like, we want to do the old blue Peter thing, here's what we made earlier, you know. We did some science and here's the result. Whereas with the LHC we've had a journey where people have seen us do it wrong and struggle from every stage, and I think that's been very helpful for us and very useful. The other thing is CERN is a very odd place in some ways. It looks kind of, it has a mystique, which is kind of seductive. The particle physicists in certain circles at least glamorous, which is not. The director of the Science Museum said the illustratively glamorous world of big science. That's not a glamour and science I've never really thought would go together like that. But it's not, that's great, all that is positive, but I think it frustrates me sometimes that people see science in the media, especially physics, and what they get is black holes and the Higgs boson and quantum gravity and string theory and all that. All the bits we don't really know, and they don't realise that it's connected to stuff that we do know in everyday life. I really try to connect, I will try and give examples of where that's connected here, and I do try and do that in the book, and that was part of my motivation to sort of demystify that we are rooted in reality. It's all very wacky and wonderful, and it is amazing what CERN is achieving, it's amazing what we're doing, don't get me wrong, but it's rooted in observational data and evidence. And also the other bit of demystifying is that the people at CERN are just people. We're just people like who've ended up doing something, we're not the Illuminati or something, whatever down around. So, okay, so I'll do the talk then. I might use this point occasionally, but I'm actually down for now because I'm going to hit my screen with it. Okay, so this is the view that I got. Is that okay? Can you see that? This is the view I got basically twice a week if I was lucky with the weather from during 2009, 10, 11 and 12 while we were starting up the LHC and analysing those data. And that's because like most of the people who work at CERN actually, I work for UCL, in fact, University College London. CERN employs very, very few physicists. It actually employs a lot of engineers and a lot of IT staff and things, but it doesn't employ many physicists. Most physicists who work there, people like me, who are employed somewhere else and go there to do the science and help build in that way. So I was living in London and commuting to CERN every week because I was leading one of the groups. Obviously, normally you don't need to do the science there, you don't need to commute every week. You need to go occasionally, but I was leading one of the groups and you need to be in the corridors and you need to be in the meetings, people come there to see you. So it wasn't very sustainable either kind of mentally or physically or ecologically doing that, but it was necessary at that time. To go there, and what this is the approach over the Jura Mountains in France. The approach to Geneva, at Geneva. This is the airport, Geneva Airport. This is Lake Geneva. That's Mont Blanc in the background there. And this yellow thing here is the path of the Large Hadron Collider. Obviously, the French farmers wouldn't let us paint it on the ground, so you don't actually see it when you're landing, but it's there. And this dotted line, which also isn't actually painted on the ground, there's a lot of channeling stones every now and then, but that's the border between France and Switzerland. So the main site of CERN is here, just over the border in Switzerland, but you can see most of the Large Hadron Collider is actually in France. Atlas is, so what's going on here is, in this tunnel, there are two counter-circulating beams of protons, the highest energy particle beams ever achieved in a laboratory. And they're brought into, it's full of superconducting magnets to keep them going around in a circle. And they're brought into collision at four places. One of them is here at SitP, one of them is in Alice, and those are two kind of more specialised experiments, so I'm not going to say any more about here. If you're hungry for more CERN after this, I advise you to get speaking to others. This area doing specific LHCb is looking particularly at matter-antimatter asymmetry, and Alice is designed for when we run colliding heavy ions, which we do collide lead ions occasionally, but most of the time we collide protons. And Atlas and CMS are the two places where the protons collide, and the experiments are what we call general purpose detectors. So they're on the basis that we don't really know what's going to happen when we collide these protons together, but we want to know everything we can possibly learn about it. So we throw all the kinds of different technologies we can to see what's produced when these protons collide, and that's what Atlas and CMS do. And I'll come on to that in a minute. But one of the things where this connects nicely, what we're trying to do is really high energy beams. So why is it so big? Why do we need such a large machine? It's actually 27 kilometres round, which, if any of you have ever been to London, is is actually the length of the circle line to the nearest kilometre, and it's easy to remember because it's yellow. It's a lot faster than the circle line, but they also collide more often. The reason it's so big, why can we do this? Why do we have to fly there? Why don't we have one in every university doing this? It's because it has to be so big. And the reason it has to be so big is the same reason that if you have to slow down when you go around a corner in a car, because Newton's law says that things that are moving, that have large momentum, will just keep moving unless you're going in a straight line, unless you act on them with a force. So when you turn the corner in a car, the force comes from the friction between the wheels and the road, and if you go too fast, then the force isn't big enough for the wheels to you skip and have an accident. In our equivalent of that is, these are the highest energy particles ever created, they really, really want to go in a straight line. So all the effort is in bending and grinding the circle so they'll come back and collide. That's the whole point. And so the limiting factor in this is not actually how much you can accelerate them and give them more and more energy, it's how much can you make them bend, can you make them go around the corner without skidding, or in our case skidding would be flying off, vaporizing your magnets and making a big hole in the ground. So we don't want that to happen. So it's the power of the bending magnets that actually limits the energy, not the amount of energy, not the amount of acceleration you can give, but the power of the bending magnets is centrifugal acceleration, as we physicists. And it's that limits it, and of course that's why it has to be so big as well, because what you want is a really gentle curve. If you try to do this on a desktop, the curve will be so sharp that there'll be no way you could ever get very powerful amount. So that's why these machines have got bigger and bigger and bigger as we go to higher and higher energy. Okay, so that's the machine, the Large Hadron Collider. Before I go on, I will come back in a moment to the detectors, in particular Raptors, which is one I work on. But I want to say something about CERN before I do that. These are the current CERN member states. In fact, this is out of date because Israel joined 2 months ago and wasn't quite fit on the graph. CERN was set up 60 years ago, and if any of you were in Geneva in, I think, September, there was a big party to celebrate its 60th anniversary. Like I said, the physicist parties, so you know, don't get your hopes too high. But anyway, they are celebrating it. So that's founded in 1954, predates the EU. It's nothing to do with the EU, except that we obviously work very closely with the EU, research council and things, and do a lot of work there, but it's funded independently and governed independently from the EU. In fact, obviously Switzerland and Norway are not in the EU, and Ireland is, and Ireland is not in CERN, and Switzerland and Norway obviously are. So it's, and also Israel, of course, it's not in the EU. It was set up basically after the Second World War, when Europe was trying to rebuild itself, and Europe was obviously a powerhouse of physics, in particular, you know, Germany and the UK and France were amazing in physics, and Italy, Europe in general, basically, and it was devastated in the Second World War. Most of the great scientists fled to the US, several of them went east as well, and Europe was just a mess. So it was set up as a non-military, neutral kind of centre to try and get people working together in Europe again after the war, and also to build up Europe's excellence again. It took a long time. It was just another lab until probably, well, certainly until the early 70s, where it made its first really big discoveries, where neutral coherence was discovered there. And the mid 80s, it got its first Nobel Prizes for discovering the leading Z boson. And it was clearly by the mid 80s, it was clearly the premier lab in Europe. But by now, it's the premier lab in the world. And if you look at the bigger map, all the countries that are called in here, not anything other than grey, is someone who has some kind of relationship with CERN, ranging from sending scientists to do science there, to being an observer state and contributing financially, and the blue ones, the members of us. The member states pay most of the running costs. We pay it for its GDP. And the UK contribution since 1954 has been roughly constant, as far as I believe, but certainly for the last few decades it's been roughly constant. In about £90 million a year in real terms is what we send off to Europe to do that, to build this, and it's been, so about £2 per taxpayer per year for this. And government after government has committed to that, and it's really something I think that the UK should be proud of as a founding member of this and stuck with it so long. I'm a Man City fan, but you know, Man United stuck with Alex Ferguson for ages before he won anything. I think it's been like that with Sterling. It's 10-15 years of investment before really any science came out, and now it's probably, that's part of why the Americans actually have more money, but they were more erratic in the way they invested it, so it hasn't accumulated in the same way as this impact. Anyway, with the sad exception of maybe Sub-Saharan Africa, we're pretty much a global thing. And my last collaboration meeting was in Morocco, which is ace, and there are links expanding into the rest of Africa as well. So that's these are the detectors. So if you go through all that effort of colliding protons together, the real key is then to work out what happened. That's why you do it. It's quite easy to break protons relatively, so we're not just doing it to break them, we're doing it to learn from it. This is the Atlas detector. It's kind of, in the book I describe it as a sort of high-tech cylindrical onion, which I'm not sure is a terribly helpful analogy. But you can see that it's kind of concentric layers of different technologies. And the beams come in, the beam comes in here, and here, collides in the middle here. And each layer of these technologies is something different. And I'm not going to go through them all now, that is another bit in the book, you find out what each of them does. All I'm going to say about it now is that each one of them tells us something special about what's happening in the collisions. And also it's quite big. These people here, to give you the scale. So it's enormous. this is how we describe it as a high-tech digital camera. One of the contributions that UCL made to this, along with Birmingham and Nottingham universities, was to design this graphics event display, which is one of the ways we present the events to ourselves. If we'd known quite how many newspapers this would have been, we might have worked a bit harder on the graphical presentation. But it's a working event display, and actually we use it to interpret what's going on. This one is kind of sliced through that cylinder. You can imagine one beam coming in from the projector, and one coming from behind the screen, colliding in the plane of the screen, and all these particles being produced. Most of them are large stuff that we don't really care about much, but you can see there are two high energy particles. Now you can actually, from this, you can tell what they are. You can tell they're high energy because if they were lower energy, they will bend. There's sort of an automatic field there that bends low energy particles. These are straight, so they're Newton's law again, same reason the LHC is big, they're not bending much, they can't make it. And they punch right the way through all of those detectors out here to registering the muon chambers, which basically means they're muons. But the muon is a heavier version of the electron. It's not so common. It's often a sign of something interesting happening in the event. And I'll show you, when I show you the data for the Higgs discovery, you'll see muons featuring at that point. But the point of this at the moment is just to emphasize one of the big challenges here. If you look at this, this is the Saigon view of this, so that we could be divided by the red spot is. And you zoom in on the red spot, these are all, you see there's more than one proton collision here. In fact, the muons are produced in this one here. There's a whole bunch of other stuff, because the protons come in bunches. And passing, there's a bunch of protons when we were running before, passing by, colliding with each other, through each other, every 50 nanoseconds, every 50 billionths of a second, 10 to the minus 9 seconds. So, now the speed of light is 30 centimeters per nanosecond, basically. So you see how big the detector is. There isn't time for a particle travelling at the speed of light to leave the detector before the next bunch comes in. Okay? And a bunch doesn't just give us one collision, it gives us, in this one's about 12, but when we were finished running, there were about on average about 25. And when we turn on again in next year, in April next year, there'll be collisions every 25 nanoseconds, twice as fast, and there'll be more collisions per bunch as well. So the data handling is phenomenally hard. Trying to work out, so remember, these particles haven't even left the detector before the next lot are on the way. Never mind got down the electric cables to your computers and even started processing them and working out what's going on. So keeping that all in time and working out which bit of data goes where and which data belongs to which collision, and then in the end, and having it ended up on a student's laptop so they can actually interpret it and write a paper with it is a massive challenge. The last stage of that is that it gets found out on a worldwide computing grid, of which every major country has a big tier 1 centre, we call them. The UK one is in Harlow in Oxfordshire. And then from there it gets passed out to the universities and then it ends up on that side. But that is a massive challenge as well. So this whole experiment is kind of pushing the boundaries in several ways, not just in physics. One of the ways it broke new ground is illustrated by this. This is a picture from 2005. This is Atlas being built. All this is now full. So it's a point, that's a picture while we were building it, or this is one of the people that built it. I realised that this was a bit special. We were trying to tell people what we were doing and say, well, is it exciting? You pay for it, so you care about it. We care about it, so we're trying to share the excitement. We weren't sure how well that would go. And I saw this in the middle of FHM. It was in centerfold in FHM. Okay, it's a bit special for buying. I don't buy FHM, so I don't buy it. But I realised that this is for a physics experiment that was a little unusual, and that people were kind of going to be more interested in this. Maybe we were as interested as we thought. Probably lots of people, maybe not as interested as we were, but certainly interested. And that was actually a very positive experience, and I think part of that was born of when I was a PhD student, my supervisor was sort of saying to me, public understanding of science, it was called then, that people need to know more, because then they'll support science models, the model right now is more public engagement, which I think is better. But he was saying this and telling all the PhD students that, and it didn't sound like it believed it really, but it was a consistent message all the way through my career, and now I know and I'm still saying it, and there's been a bit of a culture change, and in that scientists, at least in my field, are more ready to engage with it. And this was illustrated partly by the fact that the BBC were allowed in, they negotiated a deal that when we actually turned the thing on, they could go into the control room, watch it live, and they had a whole big bang thing going there. Andrew Mann and Brian Cox in the control room. Brian's actually on Atlas, he's a member of the experiment, so that's partly how it works that we managed to negotiate a deal. James Gillies, who's the head of communications at CERN and still is, fought that against a lot of suspicion and opposition in terms of why would we let the public in? Isn't it much better just to make it all work and then announce it wonderfully better? And showing people it happen in real time was controversial. I think it worked, it's been a positive experience, but it wasn't all good. This is Al Jazeera, this is me, in Al Jazeera, this guy, whose name I forget, was a professor, he was the one person in Europe who thought that we were going to destroy the world. By accident and on purpose, it turned out. He tried to sue us for doing it by accident, like creating black holes or something. But he also, during the course of this interview, claimed that we were making mega weapons as well. So we were destroying the world by accident and on purpose. I wasn't really, well, I wasn't very happy, obviously. But what had happened was I was on my way home from one of my trips, and I got phoned up and asked, can you come in and talk to us at Al Jazeera about, because I've done some Al Jazeera stuff in London. Can you come and talk to us about your experiment that's about to start, just before it was about to be switched on? And I said, all right, I thought, I was to get out and do that. I was not in front of Lake Geneva, I was in a sensory deprivation tank in an underground in an industrial estate in Geneva. I had an earphone and I could see a thing. And they sat me down and said, right, so we've got Rod Davison from New Scientist, and we've got this guy. I called him Otto the Frivolous, I can't remember his name. But, and I thought, I wonder what, when I arrived, I said, I'm so glad you could come at the last minute, the CERN had cancelled really short notice. I should have gone, why? Why? And plus he didn't want to talk to this guy. He said, well, this is media balance, right? It's everyone else and him. But actually, so I was at Reagan a week with myself and with them. And I went through the interview with it, and I was not live. And they could have edited it, and maybe look at complete, well, evil genius, or you're in the hands of the media when you do that. You don't really know. I didn't know what I looked like, or what he looked like. But they cut it, and they did actually what, in the end I didn't regret it, because if you watched it, and the feedback I got from it afterwards, there was clearly only one mad scientist on that programme, and it wasn't me. And actually Al Jazeera reaches an audience that BBC don't, and that was actually genuinely concerned about some of these issues. And I think it made them look ridiculous, frankly. And that was just, so engaging was actually better. And so I was wary about the balance thing, because I was the sole representative of the whole of physics, and he was the sole representative of some crazy energy unit. But actually, it was probably a good thing to do. And it's one of the things that I learned throughout this experience. We did survive, so it was okay. This lesson came back even more when we broke it 9 days later. So these big magnets that bend the stuff in the ring, they got very high currents flow through. They're super cool to 1.9 Kelvin. And under pressure, helium under pressure is liquid helium under pressure is still cooler. One of the joints between the magnets lost its superconductivity, developed resistance. That led to a chain reaction basically where it heats up and gets more resistance and vaporizes instantaneously. All that was bad. What was even worse was that led to a spark going over the gap, which punctured the liquid helium vessel, and a lot of under pressure liquid helium became not so under pressure gaseous helium very quickly, which is an enormous explosion. It picked these high precision magnets up with these joins and everything, all aligned to micron accuracy over 27 kilometers. Ripped them out of their concrete, they're 40-ton magnets. Ripped them out of their concrete bearings, threw them down the corridor for 1 year. Really bad. It was, and we've been all around for 9 days. It was an awful moment. I won't say it wasn't particularly bad. It was telling the PhD students that who'd come in just that year and thought they were going to get data things, going to get at least a year before you get anything. It's horrible. But we didn't go away from the media. I'd been on breakfast TV just before we started, being a smart guy from CERN. I went back a week later saying, yeah, we broke it, sorry, we'll be back. But we didn't all retreat into our shells. We carried on timely. And in a way with the media, we got very, and with the general public, I think, we got quite a good sympathetic treatment. It showed that it hadn't been staged managed. It showed it wasn't all a PR exercise. It showed you why we'd all been so excited and pleased when it did work. And people were around being absolutely gutted when it didn't, and then they did come back and they did work in the end. So I think we were privileged. A lot of scientists, when they get into the media, it's like, you've written a paper, hey, you've cured X, and then off you go. You never get the build-up and you never get the caveats afterwards. The LSD has been lucky, and it's a big enough story that it's been in the media, been following it for so long, the public has been following it for so long. You actually, although we're not typical of science in terms of the scale, we're accept that we are science, and everything's gone wrong. Things aren't quite as clear as we thought they were. And because it's such a big story, then it has, people have seen more of that in the Higgs discovery than it have in many other science stories. So I think the message for us was being engaged is actually a good thing, was probably right. And I hope it's good for more than just the particle physics. It brought with it its own pressures. The gold platform post was well out of order. I've already got people taking nuclear out of that. We don't like it. This is Channel 4 News. I wasn't even going to complain about the God particle title here. Christian Gurumef is a total professional. You know, with the Higgs boson, they often put things like the boson, that gets autocorrected to the nautical term. And on his autocorrect read over his shoulder, it had the Higgs boson. And I could see him getting closer to it, and I thought he's going to crack up laughing, or he's going to say boson, in which case I'm going to crack up laughing. He didn't, he just read it over it. I'm sure there was someone in the office having after it. Total professional. What this was there was over Easter in 2011, some people on Atlas got overexcited to be down and sent out a note around the whole of Atlas, 3,000 people, saying we found Higgs basically. It was complete nonsense. It was totally shoddy analysis. It was total lack of review. And you didn't need to read more than 3 lines into it to know that. But it leaked, of course, 3% something to 3,000 people. It was going to get on a blog somewhere, and it did. And it got into the news, just the media attention on that experimental snow line. Now, I write a blog for The Guardian, and I was saying I'm not even going to deign the oxygen publicity into this stupid rumour. But then I got phoned up by Channel 4 and said, we're going to leak this story. We're going to run this story. Will you come on? And I thought, well, what's the alternative? Someone else will go. So I went on anyway. And again, it was good because you could give people an insight into the febrile atmosphere at CERN. They're not all scientists are disinterested heroes who are selflessly working for the greater good. There are some idiots who are out for personal glory, which is basically what was going on here. I think. Allegedly. Anyway, it was a mess. It just showed you that there were disagreements, and we weren't all kind of totally honest all the time, and also made mistakes. And of course, we spent 2 minutes discussing that, and then 5 minutes discussing what we were really doing. It was again a good experience in the end. All 3 of those things, the Al Jazeera interview, the breakdown, and this thing, the leak, all reinforced to me that actually just being open and honest, journalists are actually on the public respond to trust better than I thought. Okay, we're not doing, there's not a huge amount of economic conflict or political conflict about what we do. So I'm not suggesting that all areas of science, everything would be nice if everyone was nice to everyone. But I do think that engaging is important and works and treating people with the respect to what's actually going on. We got treated with respect back quite a lot. Okay, back to the science. Why I told you that it has to be big because we want to go to high energy. Why do we want to go to high energies? There are 3 reasons. I think one of them is this equation, which is the only equation at the top. But it's if you think there's a new particle out there and it has a mass of M, then you need energy E to make it. The constant in there, C squared, is a big number, so you need a lot of energy to make new particles. And if they were low energy, you can find them already. So if there are new fundamental particles out there, then they've probably got a lot of energy. By the way, what we mean by fundamental, I'll come back to it in a moment, but what we mean by fundamental is just that we haven't broken it yet. So it's a particle that's fairly known, isn't made of anything else, and anything else is made. And that's the original bit of knowledge. But we've known about electrons for more than 100 years, we've never managed to break one yet, we've never found any internal structure to an electron. So we call it quarks in the same place. And that's an important point. That's what the mass of the fundamental particle is fixture in this equation. That mass lies behind where the equation is going forward. So I'll come back to that in a second. We also get called the Big Bang machine, or we're studying the physics of the early universe. I'm not particularly a fan of that way of describing what we do, but there's some truth in it. This is the physicist's spherical kind of universe, beige and round. That it's expanding now. In fact, it seems like its rate of expansion is actually increasing. So you don't have to be a genius to work out that it was smaller in the past. And since energy, in some definition, is conserved, that means the energy density in the universe was higher in the past. If you go and run that back to when the universe is the size of, say, a football, then the energy density is huge, and that means the temperature is high. That means all the particles in that football are travelling really fast. They've all got a huge amount of kinetic energy, and they're smashing into each other all the time, with energies comparable to the energies that we're smashing particles, a few particles together at CERN. So in that sense, we're looking at the interactions between particles, which are kind of ubiquitous in the universe. The amount of energy is not evenly known, we don't have all the energy in the universe in the mean. But we can give some few particles the energy, the statistical energy for every particle in the universe. So in that sense, what we learn at CERN does tell you something about how the universe must have developed in the first few moments after the Big Bang. My preferred way of describing this though is this one, which is what we're doing. What we're doing is we're studying the universe at smaller distance scales than ever before. Now what you're going to see in a minute, this is a water tank with water waves in it. And someone, one of my dear mates from Bonn, is going to drop a blob into this water tank. And you've got to imagine that we're trying to study the blob, and this is our detector. It's this screen here, so where the waves are going, we can work out what's going on. I don't know what this blob is, but anyway, you can see it. You can see now on the screen that there's a gap in the waves. You could detect that, you could resolve that blob, you know that there's something interrupting the waves there. That's fine. So, if the guy comes back now, puts another blob in, which is smaller, here now on the screen there's no effect. The waves are kind of reformed after the blob, there's nothing going on. And that's because the size of the blob is shorter than the wavelength of the waves. Now if you put more energy in and you make shorter wavelength waves, now you can start seeing, as the wavelength gets smaller than the blob again, you can start seeing that there's a pattern there. You can detect the blob again now, these high energy short wavelength waves. That's essentially what we're doing. We're using essentially gluons and quarks to study each other when we collide protons. But what we're doing is looking not just inside the atom of the proton, inside the atomic nucleus. We're looking inside the proton. We're actually, in principle, even possibly looking inside the quark, although it's likely that there's nothing inside the quark. But whatever we're doing, we're looking at those things at a shorter distance than anyone's ever studied them before. And to do that, we need shorter wavelengths, because the wavelength is going to be smaller than the thing you're trying to study, for that we're supposed to illustrate. So radar, for instance, is great for seeing boats and planes, but if my eyes were sensitive to radar, I wouldn't be able to see it, because wavelength is meters and we're a lot smaller than that. So, there's this correspondence between what you can see, the wavelength that we probe, and short wavelength means high energy. This is how it kind of works. So we want to study nature at the shortest distance scales, we need high energies, unfortunately, which means we need the 27 kilometers a ton. Okay. I'm going to show you the dates, then to do before I do that, I'm going to show you the bump in the plot, right? And I want to explain to you why a bump in the plot means a new particle. This is a Feynman diagram, which is how we kind of picture these, calculate in fact these collisions. What this is an electron and a positron annihilating here. This wiggly line in the middle is a photon, and then they decay again back to an electron and an anti-electron and positron at the other side. Now there's a problem with this. It happened actually in the tunnel before the LHC started. There was this positron annihilation going on. There's a problem with because of the equation I gave you earlier. There's a lot of energy here, so therefore there's a lot of energy throughout the diagram because I need to conserve. Time is going that way. So that means there must be a lot of energy here, but the photon has zero mass. The real photon, the photons you're seeing here now, have no mass. So E should be zero, but it can't be because energy is conserved. Yes, well, what's going on there? And you can think of it, if you like, as a manifestation of the uncertainty principle. In fact, you can derive the uncertainty principle from Feynman diagrams, it's the other way around. But essentially, particles that are not observed, that are in the middle of a Feynman diagram, don't have to have the right mass. You can do every line in this diagram, every vertex corresponds to a term in the equation. If you write down those terms, you find that, okay, it's a lot more likely to happen if all the particles can have the right mass, but the probability is not zero just because the photon doesn't have the right mass. These guys have to have the right mass because you observe them going in and you observe them coming out. But the guy in the middle, because you never observe it, can have, there's a finite probability of it not having the right mass. Okay, so it doesn't drop to zero. It's more likely if it does have the right mass. With knowing that bit of information, you can understand one of the most important plots. Oh, sorry, before I do that. You might ask then, why do we collide these guys? Because this has got loads of energy, so the photons are miles away from its right mass. So the chances are very small. Why would we do that? The chances of this happening are very small. And the reason we did it is because there's another particle can be in that diagram called the Z boson, which does have quite a lot of mass. When we collide it at the right mass, we can make real bonds, and there's an enhancement in the probability there. So knowing all that, you can understand this, which is one of the most important plots in physics. What this is showing you, on this axis is the energy, or if you like, it's the mass, just a factor of c² between them, it's the mass of the wiggly line in the middle of the diagram, because the photon is moving further and further away from its preferred mass of zero. And as you get towards 90 GeV though, something odd happens, it turns up and you have this kind of resonance, this peak. That peak is the Z boson. That peak is there because at that energy, the Z boson can have the right mass. And so that's what we mean when we say we discovered a new particle, actually. It shows up as a resonance in one of these diagrams. It shows up as a peak because you can calculate all these interactions, you write down all the Feynman diagrams you like. You have to somehow take them on if you can. But if there's one of them where there's a particle in there and suddenly have the right mass, you get this kind of effect of a peak because all the energy sums that up at that point. So what I'm going to show you is a peak that is a Higgs boson. And that's because in the diagrams that we use to calculate what we're doing, the Higgs boson can have the right mass, there'll be an enhancement in the mass distribution at the point where one of the particles has the right mass. Okay, I'll come back to it in a minute. So we can do that. Yeah, you see, we're just showing this to show you how high in energy we go because this is quite anti-quark annihilating in the same way. This is the 90 GeV peak for the Z, but we get data all the way up here. And we're kind of looking for what's in that particular distribution. We haven't seen any yet. These coloured ones are theoretical guesses of what we might see. It's funny how the theorists always predict ones that are just a bit too high energy for the data. They'll be right, won't they? But they were right at this. Now, I want to come back to, just before I show you the Higgs data, which is where I'll finish. I just want to show you, say something about why Higgs is important and what it really means. So, I said this bit about fundamental particles. They're not made of anything. So how do they have substance at all? I give talks on this in schools, even in primary schools sometimes. That's one of those questions that kids ask. Now, how can it be made of nothing? It's one of those questions adults ask as well. It's actually a very deep question. It turns out that all the maths, the way you put the mathematics of fundamental particle theory together, all wants them to have no mass. You can write down equations for a photon, okay, but as soon as you start putting mass in, particularly for the W and Z boson, it all goes wrong. Yet we know they have mass. And there's a real fundamental mathematical problem behind what sounds like quite a naive question. And even before we knew all the particles of the standard model, back in the early 60s, it was known that this was an issue mathematically. The reason is actually there are symmetries in the mass, which are broken by putting the mass of the particles in. If those symmetries are broken, then the mass has infinities in it, it becomes gone. You can't predict anything. It's completely useless theory. So this is a conundrum, and you already know, even before we knew what fundamental particles were, in fact. And that's what Peter Higgs and Robert Brown and Francois Engler were working on in the early 60s. And they came up with a model of how you can do this, how you can break this symmetry and give particles mass and yet still have the symmetry there in the underlying theory, so the theory still works. And it actually came out of condensed matter physics, which is what my little diagram there is. There's what this is supposed to be. I actually did this demo live at the Royal Institution, which is great. You can do it with a bit it's a bunsen burner and a bit of metal, but I can't remember what the metal is. But anyway, you take a magnet, diamagnetic, sorry?
Magnesium, normally not.
It's not magnesium, that was just Earth, that's not a neodymium is, neodymium. So it has a Curie temperature that's within reach of the Bunsen burner, so which is the point. So it's full of little dipoles, but when it's hot, they're all jigging around, banging into each other. There's no magnetic field, and everything. Maxwell's equations of magnetism are not completely symmetric. So it's a symmetric theory. As you cool it down, however, it's slightly energetically favourable for two of these to line up together. Now, if the thing's hot, they'll immediately, they might line up, but they'll get knocked away again immediately. But as you cool it down, there's a critical temperature called the Curie temperature, where two of them line up, and then because they're lined up, the third one lines up, and it's not hot enough, there's not enough ambient energy to break that alignment anymore. Suddenly they all line up, and you end up with the North Pole and the South Pole, and on this one there's no special direction. Everything's symmetric around the circle. This one now, there's a North and the South Pole, you pick the direction. Now, if you do this a million times, the direction could be anywhere. There's no special reason it's there. It could be anywhere. So the symmetry's still there if you've done the experiment often enough. But for a specific magnet, you've broken it. You've suddenly made a North Pole and a South Pole. That's essentially what the Higgs theory does. That's how the Higgs theory breaks this conundrum between having a symmetric theory but breaking a symmetry in everyday life, because we know that particles have mass. So there's a temperature in the universe where you cool down and this Higgs thing, this happens, the analogy of this happens. Now there's something you can say, that's a neat idea, but what are the physical consequences? Can we prove it? Is it just a neat idea? Well, the consequences of it are that there is a field, right? A magnetic field, a net magnetic field. The analogy of that is a Higgs field filling the whole universe, which is a pretty bold claim, just invented a field that fills the whole universe to explain your maths, get the maths right. And the reason Peter Higgs's name is on the particle, even though actually Brown and Engler were first with this model by a month or so, is because he said, and if you've got that field filling the universe, you'll know it's there, because if you snap the field really hard, it'll make a ripple in it. And so you imagine displacing one of these, so the ripple passes through the magnet. And that ripple is a Higgs boson. Because you can't find, this field is everywhere, you can't take a bit of the universe where it isn't and compare it to a bit where it is. And so notice the difference, because there's no bit where it isn't. The only way you can prove it's there via data is to hit the universe really hard, which is what we do at the RC, and make a ripple in it. And that ripple is the Higgs boson. It's a quantum excitation field, but it's very good analogy to the ripple in this background magnetic field. That Higgs boson will have a definite mass, and that will lead to a bump in the data. So when you hit protons together, one of the things you see is photons coming off. These yellow blobs are the energy of photons. If you see the bigger yellow blobs, this one here, this one here, collect a bunch of those events. One of the ways a Higgs boson can be produced, and it will decay to 2 photons sometimes. You collect them all, you look at their energy momentum, you say you hypothesize if they came from a particle, what would its mass have been? You plot that mass, which may or may not be a new particle, we just plot it anyway. You get a plot very much like the one I showed you before, only animated. 2 years of my life going past, look at the top corner there. This is the mass, just like it was in the other plot, and this time the mass of 2 photons. This is the number of times it happens. You can see we're looking at this, I'll run it again in a second, but we're looking for bumps. And when you run your statistical analysis on it, there is a bump there, and it didn't go away. I want to run it one more time just to show you. So that is, see this? That's why we lost our sleep over Easter. This was that big bump in the day, which just not statistically significant. Rubbish analysis went away. But you can see with the media attention and all our own excitement, never mind the media, it was very hard to discipline yourself and not think, oh, get the Higgs up. There it was. Even with all that, I was in Westminster, I saw, on the 3rd of July, I saw our practice talk, Fabiola Nazi, who was our spokesperson. She gave the talk, a practice talk on the 3rd of July in CERN. And then I flew home that evening because I was going to be in Westminster when the Science Minister was to do the UK end of this announcement. And although I knew all this, my opposite number, Jude Verdi from Imperial, was there for CMS to do their experiment. We hadn't seen each other's data. We heard rumours obviously of that, but we knew our own data was moving all the time anyway, so we didn't really know what they had in the real. I'd say there were many moments where I think I suddenly knew the Higgs, but to me, one of them was when I saw that CMS had the same book. This is a completely independent experiment, completely different technology, but the book in the same place. And it was such a relief, I tell you, to see it in the same place and know that Jim and I knew solved the first time the final data from each experiment. We'd actually got something. I mean, the numbers slows, we definitely got something anyway, but you need an independent experiment for those who don't really believe it. And in fact, we did better than that because this is another way of representing the events. This is an electron and a positron, two muons in the detector that I mentioned earlier. It's another way that Higgs can decay into these four particles. And again, you can hypothesize as a and narrow out what the energies. And plot it. And here you go again, same story. The background is a lot smaller. The bits that don't involve the Higgs are in red, the theoretical model. And you'll see there's a bit there that the theoretical model doesn't track. The background here is a lot lower, but it's a lot weird shape. Weird shapes, which you understand. This is the Z photo again, actually, now it's a GB. But there's a bit there that clearly isn't modelled by the background. And if you zoom in on it, which I will in a second, then you see if you put in the expectation for Higgs boson, there's some mass it roughly gets it right. And that's actually, again, about 125 GeV mass, which is where the two other books which have been loaded completely independent experiment. And also CMS had that too. The unnamed version test here, and they even put the Higgs in for you. This is what you'd expect for the eventual Higgs boson that we did find. You can see that it can track the data. Although while we were collecting this in real time, obviously we didn't have the rate on there, we didn't know the answer already. So basically this is when we announced that there were basically four independent experiments. They're basically books in plots, which is why I showed you the Z book in the initial plot. And that's because there's a Feynman diagram describing the process, and somewhere in the middle of that Feynman diagram is a Higgs boson with 125-ish GeV of mass that can have the right mass and leads to an enhancement. Okay, so you crunch it through your numbers through in case since you're all skeptics. We set a Phi Sigma fairly arbitrary threshold on what we call a discovery, which is in principle the probability of 10 to the minus 7 that we're wrong. But we do a lot of experiments, so we want to be really sure, and also you make mistakes with algorithmic uncertainty. So 10 to the minus 7 is really, it's basically an ad hoc diagram, but it's something that's fixed and stuck to. So we did, and that's what we passed on the 4th of July. But in fact, now if you take that mistake, now it's well below 7 sigmas. The probability of being wrong with more than less than a trillion, and that's only accuracy. You can square that again to get if you put CMS in Z, similar level of confidence. So it's definitely one of the fun things about the announcement was everyone was saying, have you found the Higgs boson then? And we were all really pleased and excited, so we definitely found something. And from our point of view, that was the exciting thing. There was something fundamentally new today. It looked very much like a Higgs boson, a standard model. But we didn't know enough at the time to say for sure that's what it was. What we wanted to say was, this is amazing. There's a book in a plot where no book should be if there's no Higgs or something. It was a new fundamental particle. It did pan out as we did more measurements later that the influence of W and Z in the way that it should. It has all the right properties. So whether or not it's a standard model Higgs boson, you'll never be able to say for sure. You can only say that as well as you measure everything. That's true of any measurement. But we know enough now to know that it does interact with the W and the Z boson in particular in a way which implies that it's connected with the origin of mass, which is enough. It's why it has a density, if you like, like Higgs. And it's quite amazing that in 1964, those three guys, those six people actually, came up with this theory based on those abstruse mathematical ideas, and then over 50 years later we found it up with the plot because they realised the connection. I find it quite amazing. And there's nothing else like the Higgs boson in the standard model. It's not just another force, or just the qualitative than anywhere else. And it popped up in the day. It was an amazing experience. Peter Higgs was asked afterwards what he did to celebrate, and he said, well, I couldn't really, I had to get on the plane. Although he's a big real elf on Peter Higgs, and he said, what, did you have champagne or something? No, we had love and pride on the plane. So he drank that. And, because of that, when they opened the Science Museum exhibit on the Higgs, on CERN, which is just moved to Manchester, it's well worth seeing if you get a chance. For us, actually, it's Professor Peter Higgs. Can't think why it's blurry. I think I must have had one or two. But they made like a few thousand of these bottles, and we were drinking away at this really great event. Peter Higgs was there, and Stephen Hawking was there, and all kinds of politicians were there. And we were having a good time, and at some point realised that every bottle was a special Peter Higgs bottle of blood and blood. He also got the Nobel Prize as well, but really, that's all I have to say. But I think it was an amazing journey. I have my little books in the back, whatever. But it's been very special times to be a physicist. I think one of the things. Well, I hope that in the whole story of this, that what this Higgs thing is amazing. But I also think I hope we take the opportunity to show people what it can be like if science is actually engaged with the public, and also show people that what it's actually like doing science, which means it goes wrong sometimes, but in the end it usually works. That's great.
Right, thanks John very much for that. We're going to have a 15-minute break now. We'll come back for Q&A afterwards. So if you're not back by 22, you're going to miss out on the first part. And hopefully we can find out what Higgs is going to do for us. I know what electrons do for me and photons, but I still don't really know what Higgs is for. So that's it. So make sure you're back by 22, because trying to keep it last time wasn't quite distracted here.
Yes, so if the microphone fails, then do tell me and I'll repeat things. Yes, first question over there.
Hi, right. I'm sure there are lots of technical questions that will come along in due course, but I'll start with a really basic one. Why is CERN where it is? Why is it in France mainly? Is it for political reasons? Is it for, I don't know, I'm sorry, and I've got a second question which is sort of related. Why is it only 27 kilometres in having a big one make it 54?
Right.
Or 1,000 or whatever?
The answer to that one is money. There are actually the tunnel was built primarily, so that's the wrong bit. I'll come back to the first question. But the tunnel was built to do the Z boson that I showed, so with electrons and positrons. And they actually the energy limitation in that case also comes from the sharpness of the curve, although for a different reason. Because of synchrotron radiation, you lose energy on the curve. That doesn't really matter. But the point is that the bigger it was, the higher energy you get. And with the magnets and the amount of energy they could pump in, then 27 kilometres was what they knew they would be sure that they could get to 90 GeV and make a Z boson and study that to death. Now that was actually really important. That told us, for instance, how many neutrinos there are in the universe. So that's why, although even back then they knew that they at some point would want to put, when I say they, this was back when I was in Naples, so they were talking about this in the late 70s, first discussions, early 80s. Okay, I wasn't in Naples though. I wasn't paying attention, that's for sure, to what they do. But so I'm rehearsing what I've been told by older people. But they definitely made the tunnel wider. So 27 kilometres was they wanted to stretch their budget as far as they could, and they make it as big as they could. But the only thing they could justify was big enough to make the Z boson on the current technology. So they fixed it. And they made it round enough, big enough to bore the tunnel, so that they could put a proton beam in the end afterwards.
I seem to remember reading somewhere in the States there's an even bigger. tunnel that's planned or being built, or has already been built?
In Texas, they were building one, they never finished it. It's one of the, as I said at the beginning, one of the problems, one of the benefits Cerner's had was it had less money than the US per year. It had a much more stable planning basis and much more broader commitment, longer term commitment. And that's why we went to build the LHC. The SSC in Texas would probably have been a better machine if they built it. But they didn't. They spent I think several $billion on it and then cancelled it. So, and then that's why they all got concerned. So, the first question about why Indonesia, I think, although I don't know, there are two reasons. One is that geologically suitable because you want rock really stable. And so, you're kind of in a flat bit between Jura and the Alps, and it's a fairly stable area. The other was political. It was really set up as where in Europe can this happen. Remember 1954, it was, the idea was that it would unite Europe. Of course, it didn't really go across the Iron Curtain in the end, although they did, the JM and Putin and Russia did collaborate. In fact, if it wasn't for Ukraine, Russia might well be a social empire. They know obviously. During the Cold War, we did always work across the Iron Curtain. In fact, I went to a CERN USSR summer school just before the end of the USSR, actually, in Malaysia and Crimea. So we were working together, but not, they were never members, they never really joined in that sense. But I think Geneva was the European neutral space as well.
Forgive me for paraphrasing, I'm not getting my facts wrong, but there was something a couple of years ago where one of the scientists said that if this physics is true, I'll eat my hat or
be Jim.
And what was that about? Did he have to do like a media-friendly thing like that just to say, look, we're wrong about this, but I want to put it in ways that you understand how wrong we are?
First of all, your question is way too naive because it wasn't his hat, it was his shorts. It wasn't my style, I have to say. So, okay, the question was, I think what we're talking about is when an Italian experiment that uses neutrinos from CERN, so I make the point, it's not a CERN experiment. The BBC did declare it as a large hadron collider at some point, but it wasn't nothing to do with us, and very little to do with CERN actually. But they declared that neutrinos are traveling faster than the speed of light, I think is what you're talking about. And Jim Appelidi went immediately and said, if this is true, I'll eat my box shorts, I believe. I was also responding to that, and my attitude was, this is very exciting and true, I don't really think it's true, but let's look at the evidence. And I was involved in the program with Marcus de Sosa, where we went through what they might have done wrong. It turns out what I thought they'd done wrong wasn't what they'd done wrong. What they'd done wrong was much stupider. But they were wrong, and Jim, I sympathise with him, and I think he was probably prepared to eat the shorts.
The reason I ask this because I spoke to many theists who use that as a point and say, well, look, this is how wrong scientists can be, so if they're wrong about that, they're wrong about everything else.
Wrong about in what case? I mean, he wasn't wrong. Right?
No, what you're saying is because they were arguing amongst themselves. This is what I was told. This is saying the scientists saying this happened. So the scientists saying no, that's not true. Which is obviously that's how they hold it anyway.
Yeah, and the question is, how do you decide? Is it because you learn all the people you disagree with, or is it because you get some data? I mean, you've got to be on the data. To me, I think that. I get much more nervous about the tendency of scientists to preach from the pulpit, and I don't think Jim was doing that. I think he was saying that he had there was the theory of relativity and the fact that the speed of light is an observational maximum and is built into our theories of reality so much that one outlying result isn't going to change that. You need it confirmed. This is basically what I was saying, and he was saying, well, I'll eat my shorts and it's not fair. And it's fair enough. It's not the way I was doing it, I must say. I didn't like people dumping on the result immediately. was wrong. It has to be wrong. I didn't know why, but I knew it had to be wrong. What actually was wrong was because they hadn't plugged the cable in properly, by the way. That was really rubbish. And what was interesting was that it stimulated a whole bunch of scientific papers from theorists saying, okay, it's probably wrong, but if it was right, this is how it might fit with what we know. And actually those things are kind of interesting. It's like, science is the kind of spotlight of effort moves around, and that is dictated by human prejudice and things, and politics and finance and all kinds of other stuff, and we shouldn't kid ourselves on that. But it's kind of interesting that if they had measured it to be the speed of light, you would never have been. Confirmation bias is huge, right? I mean, actually in this case it's the other way around. It's like, if you get the wrong answer, suddenly you're all in the news. In the book, actually, I say experimenters get the news when they're wrong, and theorists get the news when they're right. That's the way it goes. What over there?
Hi. Obviously, this is all quite cool, but what does it mean? What are you going to use it for? What's the future?
Use it. It's not about, I don't know, it's a simple answer. Every time we human beings, not we physicists, but we human beings, find out something new about the way the universe works, we usually find a way to exploit that information. But that's not why we did it, and I haven't got a clue how we're going to exploit it. I can think of all kinds of sci-fi possibilities, but they're all going to be wrong. I don't know, if you understand the origin of maths and then we find a way of manipulating it, which is what we usually do when we've understood something, then it would be great. You could get all kinds of. I'm not so certain. But I don't even know how to start manipulating it, that's the problem. So it's all kind of incredible because even to create things basically use a machine like that. So maybe it'll be at least a decade before it's in your iPhone. I really don't know. But I would point out that you do use the World Wide Web, and you do use touchscreen technology, and you do use antimatter, and you do use superconductivity, and a lot of superconducting cables specifically came from CERN. All the other three things also came from CERN. So, and by that I don't mean to claim that CERN did 100%, although pretty much did use the World Wide Web. Technology. But it's part of an ecosystem of science. So I get equally impatient with people saying, what's the point of what I'm doing, as I do with people going, hey, you'll just do applied science as well. So it's all good and it's all part of an ecosystem. And we use applied science and we benefit from applied science and they benefit from what we're doing. You need that kind of stuff going on, and as a whole then you benefit from that usually. So it's easy to appear to apologetic and to arrogant, and I think really I like the ecosystem. I'm head of the physics department at UCL, and we have people working all the way from totally close to market stuff from quantum mechanics to stuff I've been analysing physics, which is really kind of the knowledge of people is probably useless, but bloody cool. It's stuff that we like being in the same department. There was another question. One there, I've not seen that happen first before. One there.
Well, I remember some years ago, one of the concerns was that miniature or micro black holes might be manufactured by the collider, and I wondered what the official response was.
It wasn't just a concern, Stephen Hawking was betting on it. Yes, there are models where, which essentially is a crisis in physics at these energies. Either you find a Higgs boson, which is a fundamentally new kind of thing, not just a new thing, but a new kind of thing, or something else happens, because without the Higgs, nothing else works. And one of the alternatives was that actually there are extra dimensions in space-time, which you can't see, they're kind of curled up small. You can't see them until you've got a lot of energy, and we might see them there. And if that was true, then that would mean gravity would suddenly come into the standard model of particle physics, which is the particle physicists kind of ignore gravity, because we don't know how to deal with it. So that's where this would come from. If you have extra dimensions, then the energies we would be at, that even the tiny masses of two quarks, we'd get them close enough together that they would form a black hole. Now the same theory said that it would immediately decay by a Hawking radiation, which is like it's obviously making a black hole in the universe sounds like a bad idea. In fact, that's what Otto Friedman was concerned about, or claims to be concerned about. I don't really believe, I don't trust theorists at all. So, no, I mean, I trust, it's sometimes right. But we knew it wasn't going to happen very soon, and this is going to say what's the response. We actually did a safety analysis, health and safety, trying to check on how we're going to destroy the universe with black holes. And it's on the archive, which is where you get all of these things for free. It's there, ARX on it, it's very good. You can find it. John Ellis is one of the authors, who's one of the lead theorists. And one of the most compelling reason is that if it was that easy to create a big black hole, then no star would ever last, because there are very high energy particles flying through the universe all the time. They're bombarding the Earth and the Sun and neutron stars. However dense we want to make it, we would just see way more random black hole formation happening if one of these little black holes could actually form and get out of control. So we would not even be able to build a LHC if that was possible, if it was capable of destroying the universe. To me, that was there's no theory, there's no quantum mechanics in that theory, there's just statistics. And I like that, so I really did it. So we did put that out there.
So the energy level that are nowhere near big enough to create one.
Yeah. I mean, the universe is pretty robust, right? We might be able to destroy the Earth, but doing something like bringing black holes is crazy. When I say destroy the Earth, I mean nuclear weapons and all this stuff. There's too much. We can see too much of the universe to know the catastrophic events like that. We're not going to realise. I mean, we boast about, actually we did moderate our language because we were going, isn't that highest energy collisions ever anywhere? And we said, no, actually they're not. They're happening in the atmosphere all the time. It's just that we're doing it in a lab where we can measure what happens. But if what happens is something that you would notice even without Atlas, like black hole in the soil of the world, then we'd have seen it.
You mentioned that you're making decisions every couple of billions of seconds. I was wondering what kind of computing power you can use to record this stuff.
Yeah, it's enormous. I'm not a computer scientist, so I probably don't know the numbers right, but we have I'm trying to remember how many processors now, but there's a tier 0 centre at CERN with thousands and thousands of processors. It's kind of interesting that most of it is actually commodity computing, because it's not highly parallelized, so you don't need a lot of shared memory if you're a computer scientist. You can basically pile up Intel boxes and do it, but they're big piles. So how well it costs about £1 million a year to run the thing, how well in terms of power and content will it break in machines. I don't have the number in terms of spec units or whatever.
Do you have sensors that can respond at pretty much the speed of light?
What we do is that we have a series of what we call triggers. So we have online, we're looking, there are so many events going on, we can't even record most of them. We record a tiny fraction of them. So then you want to be very careful that we're not just biasing ourselves by the point we look at. So most of them are very, say, build events, they're ones we've got billions of already. So we kind of have online systems to see whether this has anything that distinguishes it in any way from those very build events. So even the new one being produced will be enough. It's fine at a very low level. But if something gets through to the muon chamber on the outside of the detector, it will stay with it. And those are online, they're ASICs and they're real hardware algorithms. They're not at all. So they're application specific experiences. So they're really fast. And they're doing a very simple job very, very quickly. And while that's all going on, the data is in a buffer, it's stayed in a kind of a call it a buffer. You put the data in and it clocks along like this, and if at some point one of your little algorithms doesn't keep that one, then we read it out and save it, and in the end it drops off the end and is lost. If you don't do that. And then once it's been saved, then it goes to another level of similar, increasingly have a series of classes.
So many questions, I don't really know where to start. But in what way do physicists think that the Higgs is responsible for mass?
In the way that it, the mechanism is that there's this background field in the universe, which is by field I mean it's essentially an energy field in the universe, and it's by interacting with that. So there's an analogy. What, another analogy?
Yeah.
Okay. So it's David Miller, who's a guy who tells about the commitment, lots of commitment of governments, by the way. One of the Waldegrave, who was a science minister, when this was approved back in the early 90s, the Tory government. Most of it was funded through the Labour government, and then David Wallace was there at the end with the stuff. But he put a competition out. So if any physicist can tell me a way I can understand what the hell exactly the answer to the question is, then I'll give them a bottle of champagne and maybe we'll fund it again from the IC. I think they were going to fund it. It wasn't. He was a good guy actually. He wanted to know the answer. So they'd already decided to fund it. But this analogy became always the cocktail party analogy. Anyone know the cocktail party analogy for Higgs? Yes? So we manufacture it again. So yeah, exactly. We manufacture it is why it wasn't properly. But they, so actually it was earlier than that, because that's what still going. So anyway, the idea is that you imagine a cocktail party full of people chatting and gossiping, and there's someone who is famous comes in. So I've seen this done actually brand costs. It was manufactured in the initial analogy. And as soon as she comes in, everyone's around her, like flies around manufactured. And she can't get to the bar. It's really hard to move through the room, it's really hard to change the record. Whereas someone comes in who no one's ever heard of, then they just get straight to the bar. It's pretty stupid. The cocktail party people in the background field in the universe, the amount of famousness is the amount of mass you have. So it's this kind of interaction with the background field. And the best thing is you can even do the analogy of the Higgs boson, because someone pops a red round and goes, manufactures on the way, and people push back, what is all this saying? You get this little knot of people traveling through the background field, and that's the Higgs boson. What the hell is it?
What are the upgrades? What is the need to look at, and when will we get
right. So if you couldn't hear the question back, it was the galaxy's closed now for upgrades and what's going on, what actually are there. Actually, they're not really upgrades, to be honest. We're fixing it so we can get to our design energy. So when it broke, the whole thing is cooled. It takes a lot of time and liquid helium to cool it. And so when it broke, they went through to see how can we stop this happening again, and they found 2 or 3, it's in octants, that 8 independent sectors, and it was one of those that blew up. In fact, it's the last one that the commission blew up. And so obviously that one has to be prepared, but is this going to happen again in any of the other 7? And they went through and looked as close as they could, but the thing is it's all cooled down to 1.9 Kelvin, so you can't actually get in really too close. And if you do, you get to warm it up, and that takes 3 months. And then you do what you want to do, and then you cool it down again for another 3 months. So you do them all, and you don't have time to do anything. So they looked at them all, and I think they found 2 others that needed attention. So they warmed them up and went in and sorted them out. And then what they could do, they were testing kind of whether these things are developing resistance and whether that problem was ever likely to. Very hard to work out what was actually going on. And so after it blew up, I think half of it at least has not actually been really made more robust against that problem. It's just that the tolerances are such that it didn't happen. So what they need to do is really warm it all up and do it all properly. So there are multiple failures with this blowing up because not only should the joint not fail, the welding doesn't fall. but it should have been protected. You can protect things against this sort of claim. It's called a French when something develops resistance. You can protect it and jump all current off somewhere. The joints were not protected. That's the exact fault. And then you could have defended the spark occurring as well. You could close it. It was, as with any big problem, it's not just one mistake. It's like a system failure. So we could fix some of those without going in there and making it warm again. We can fix them all. So they're going in there and fix them all. So it will come back at full design energy. Now while that's happening, we are taking points of repair, maintaining upgrades and the detectors as well, but the main thing is what so. Yeah. So what do you first think? So,
you said a few minutes ago there are other dimensions in space time that are like small.
I didn't say there were, I said there might be.
I understand dimension as being something sizeless, in which things can be big or small. So what on earth do you mean?
You got to think that, so you think of that's all these things have to go to a lower, you can't picture it, all you can do is difference. But the best way to picture it is to drop to a lower number of dimensions and think what would it mean in 3-dimensional space, in 2 dimensions. What was if there was a smaller 3rd dimension, right? So if you were living in a flatland, and all you knew about is 2 dimensions, I don't know, there's a 3rd one, but it's still small. It would just mean that it doesn't mean that your 2 dimensions are built. Right? It means that if you've got a 3rd one, it doesn't extend very far. So you never actually it's like a piece of paper and you damage the thickness unless you get to a certain. You can't measure the thickness of the piece of paper because your wavelength of any energy you never got to, like the video I was showing, is longer than the thickness of the paper. So you think you're living in 2 dimensions, but actually there's this 3rd dimension that's just really small. Not all you ever see is things moving in 2 dimensions. If you get to a certain energy, then you can start seeing the thickness of the paper, and that's what it means. So I mean, it's very, very hard to picture. As with a lot of these things, you write down maths and you look at it and think, I don't know what that means when the maths works, and then you can't gradually get used to it. And actually, it's one of the things science and maths do for us, is allow us to get used to new ways of thinking about stuff. I mean, a lot of the stuff that we take for granted now, was very counterintuitive.
So the dimension itself is small, more that it would take more technology than we have to see.
Well, they're connected, because the fact that it's small was originally on the ceiling yet. It's not that you suddenly head off right now to reality, it's the fact that it's really the wavelength video that I showed said that you can't see things smaller than the wavelength, which means, and the small wavelength means a high energy. So if you don't get up to a certain energy, you just think you're living on a piece of paper. When you get up to a high enough energy, you say, oh yeah, but I can see this paper's got a thickness because my wavelength is small than the thickness of the paper. And you suddenly start seeing that. It could have been that at the LHC we broke that energy barrier and we could suddenly resolve these extra, almost super thin. I mean, thin is better than curled up, to say. But you can have any of them, so then they have to be curled up. It's kind of, that would be what it is. So it's the two are related. It's the fact that it's small, and that because it's so small, you need a huge amount of energy to even know it's there.
Right.
So with the talk final part, so class 1 is class 4, which turns into a class 4, which goes back.
Sharp it up.
Yeah. I didn't quite understand what was the connection between the photon has no mass, so by mass energy equivalence, how it should have the energy. But it's not sometimes the photon.
So, okay, so I'm sure you're not the only one. The photon is a particle. So the first thing to deal with is that particles and waves are both classical analogies for what's going on. So the answer to is it a wave or a particle is neither. It's an excitation of the quantum field, which is not a very technical phrase. So it is fair enough then to fall back and say that you have to work appropriately like a particle or a wave. And in this case, it's more appropriate to treat a particle, a photon like a particle. Okay? And they do behave like waves sometimes. All particles, the electrons behave like particles sometimes. So think of it as a particle, don't get it. It's wiggly line, just it's the way it's a convention to show you that it's a photon. So the point of this just is that these are supposed to be, these are real particles that have been accelerated around 27 kilometers in that tunnel, an electron and an anti-electron, brought into collision, they collide here, and then we don't know what, and then something happens. So in terms of observational science, there's a block there, we don't actually observe it. And then what we observe is where this came out and this came out, and they came out in some direction and with some speed away. And the block in the middle is the way Feynman wrote down the idea of calculating stuff, which is on field theory, Feynman and others. And we don't actually measure it, it's a calculation tool. So it may be that there's a better way of thinking of this, but this is the way to think of it. It's not just a cartoon, it's that every line in this and every vertex has a corresponding term in the equation calculator. But the point is that calculation tool or not, there's energy here, there's energy there. If this tool's going to work, you have energy in the middle if the mass is zero, and the answer is the mass isn't zero in this tool. And if there are physical consequences of that, which is why the tool works, in that when the mass is the right mass, you get faults, when it's not, you know.
So, how does that relate to things you actually?
It relates to, so the question was how does that relate to the thing you actually detect? I think it's a fair question. It relates to the fact that, so we measure the electron and the positron in the detector. We know the angle they're going at and the energy they have. And that allows you to reconstruct what we call the invariant mass of that pair, which should be the invariant mass of this thing in the middle.
It's those two on the right.
It's these guys that tell you. It's these guys that tell you.
Right, okay.
These guys tell you, for illustration purposes, this tells you there's an energy conservation problem because there's no as well as energy here. But what you actually measure on the way out is these. And you put together their energy momentum saying if they came from a particle, what would its mass have been? And you can do that. And then you plot it, and if there's a bump there, it means there was one half of that mass.
What's the next big thing that's being searched for things?
To be fair, there's nothing that's universally agreed as to Higgs. I think that was so on our to-do list, we said nothing but we had to. But my personal big thing next is dark matter, which there is good observational evidence that we don't really know what's out there in the universe and rotational curves of galaxies and the way light bends in distant stars and galaxies indicate that there's a lot more gravity there's a lot more matter out there that's interacting gravitationally than we can actually see. And there is no, so while the standard model is sort of complete with the Higgs boson, it doesn't include dark matter. There's no candidate particle in the standard model for dark matter. Neutrinos could be some of it, but they're not right, and they travel too fast and not enough. So there's a new particle or something out there, and that's very compelling experimental observation evidence that was got to do, and I'd love to know what dark matter is going to do in that career.
Are there any theoretical ideas of what energy is?
There are, but they're not as concrete as the other Higgs. So one of the lovely things about that matter, as opposed to Higgs, is there are three different ways you can look for it. So one is we might make it with the Large Hadron Collider, and I think theories like supersymmetry or some of the extra-dimension theories predict dark matter candidates that we might be able to create with the Large Hadron Collider when we go up to higher energy, which would be great. You can also look for it in, there's some really sensitive experiments, usually in mine shafts, really underground where there's not, you're not being bombarded by cosmic rays all the time. Just looking very sensitive to if there is that matter out there, that we're moving through a cloud of it right now. So every now and then we'll see a little vision. We've got that quiet enough to think we might see those, so we're doing that. And also, if there is that matter out there, it will come together in the middle of galaxies or maybe even in the middle of stars. And then sometimes a dark matter particle might hit each other around it. You might see hydrogen particles coming from the centre of the galaxy at the side of the dark matter. Three completely different ways of looking for it, all with their strengths and weaknesses. What I really want to see is all of them go consistent answer and find out what it is. So for me, I probably quite a lot of physicists and astronomers, that's actually the priority. It's very hard. We were very lucky with Higgs in that we knew if we didn't find it, then it wasn't there. There was no way we could go, we needed to get a machine. It had to be there if it was going to do the job it was proposed for. Whereas dark matter is more slippery than that. It's hard to, can't get, if we don't find it at the LHC, it doesn't mean it's not done. It could just be really a machine.
You spend your life studying the nature of it's not true thinking about how this matter gives rise to consciousness.
I have the luxury of it, but I don't really have any contribution to that, I think. We had a TEDx thing last year, a bunch of talks, and this guy, Jon gave a talk there, which impressed me. But I don't know yet whether we're... So I'm very interested in it. I'm very aware that what we do, we build very complex experiments to make our life easy, basically. So we're a very reductionist approach to looking at what the underlying laws are. If we really understood, if we had a theory of everything, it wouldn't be a theory of everything. Right? I mean, if we could write down fundamental physical laws and all fundamental laws, and it's not the self system, gravity, it told us what that matter was, that energy, and everything else. It wouldn't explain even, never mind consciousness, it wouldn't explain biology. I mean, in principle, QED, quantum electrodynamics, explains the whole of chemistry and biology. My wife's a chemistry teacher, always that I say that. But it's in principle, emergent behaviour is interesting, and reductionism is one. The reductionist approach is really valuable, it's really important. It tells us what the basic building blocks are, it's not the whole story. And consciousness to me comes under that. And before I understood consciousness, I had to understand genetics properly and all the rest.
I understand that many physicists subscribe to the notion of supersymmetry, but there's either little or no evidence to support it. So I was wondering, is the LHC ever likely to provide any evidence? And if it isn't, what physicists do in the absence of any confirmation of that theory?
That is the question that is exercising a lot of physicists. There are three reasons, so everything you said is correct, and then to answer the question. So the question was, a lot of physicists have been and were fans of supersymmetry. What's it for? And if it's not there, what do we do? So there are three reasons people like supersymmetry. One of them is that it's very hard to explain the consistency of why the Higgs mass is where it is. If there's no fundamental scale in nature, why, then quantum corrections tend to make the Higgs mass go really high, and you end up with a theory that looks like it's been fine machines, some very bad and decimal places. Looks implausible. The other reason is that symmetries in nature have been very good in mathematics, have been very, very useful as a guide to understanding nature. It's worked many, many times before. Supersymmetry is the only one that we haven't actually seen in nature, so it's kind of natural to assume that it might be there and give us a clue. And the third one is that it provides context for dark matter, so with stable superclasses and some superclasses. Now, the dark matter one I never really believe much because most theories that we haven't seen yet give you a non-interactive particle that could be dark matter. The standard model fine-tuning argument, I'm not sure, I'm not qualified, I'm not a physicist, so I'm I'm not really qualified to say, but there are people out there now saying actually this is such a big problem as we thought it was. The standard model is self-consistent within itself. It's only when you start worrying about gravity that you start to worry about another really high energy scale, that you see this as a problem. So it's a bit of a subjective problem, to be honest. I'm not sure we've really got to the bottom of it. And there might be assumptions with the standard model, but it's not a problem. But I'm not really qualified to say absolutely my opinion. And the symmetric principle thing, that's fine. I buy that and it works. But that doesn't mean it has to be anywhere near the LHC energy. It could be radical between stuff. It doesn't matter where it is. So I think that if you don't find evidence of supersymmetry with the next one of the Untitled Chapter, it will become a lot less fashionable. It will not be, you can never rule it out because it's too separate. It's not confident, I think it's predictions. But the idea of supersymmetry being anything to do with what we call the electric symmetry reference scale, which is where the Higgs and W and Z and all these masses of fundamental particles exist. The idea of supersymmetry being anything to do with that, I see that as a possibility. So it won't be definitive, but I think it will shift the gravity of theoretical thought significantly.
Just a little bit of my last article, from your book and your stars, and I was thinking about whether there was like constellations and all, but is it big?
No. Well, not as far as I know. And to be honest, I'm a novice in this game. Right, it's my first one. No, they sent it off to the designer, and he came out with that and said, "What do you think of this?" And I said, "That's brilliant. I like those constellations." I should ask the designer what it is, but I suspect he just did it.
Just take very one last. You said at one point in the lecture that you lot should know this because you lot are skeptics. Would you not consider yourself a skeptic, or do you not understand maybe what we think of ourselves as skeptics?
I consider it. I've attended skeptics meetings before I talked to them, so I'm fairly skeptical about stuff. Yeah, I mean, science, reason, and critical thinking is what it's all about. I don't always talk to those kind of audiences, so I've never yet talked to an audience where I said, "Well, the Big Bang Theory," which I like to say that. Okay.
So, there's all these fundamental particles. How confident are you that they're actually fundamental?
Not. I'm really not. So one thing that is in the book that I didn't say tonight is that most of the mass in the universe is nothing to do with Higgs. It's to do with the binding energy of quarks inside protons. Most mass in the universe. Okay, that matter might be to do with Higgs, so in that case, the Higgs wins. But the matter we know about is mostly body of protons and neutrons, and their mass mostly comes from the binding energy of the quarks inside them. And there are plenty of theories that say the mass of what we think of as fundamental particles is just down to the binding energy of something else more fundamental than the circles all the way down.
So how many fundamental particles could there be? I think someone mentioned 16 earlier.
Well, in the periodic table of particles, right, we have 6 quarks and 6 electrons, and that's fairly orderly. And we have the W and the Z and the photon and the blue one carrying forces. So that's 16. And we have the Higgs and the 17. So we have the 8. And that doesn't include gravity, so we don't know what's going on there. Linear gravity, and they're all mass particles, so most of them, all the 6 particles. But it's still pretty orderly, right? Come on, everything else in the universe is made of this, and then
there's quite a lot. You say everything's really like what's happening.
Yeah, but they're related by subjects. So they're incoming. So there's an electron and an electron neutrino, and there's a heavier version of that, and then one more copy. So it's quite orderly. It's not, I mean, yeah. So there's a lot of free parameters in the standard model. the oldest it's the first subatomic particle. It's split the atom when it gets electrons and nuclei, first of all. And that was more than 100 years ago, and as far as I know, there's nothing inside it. But that doesn't mean that that's forever the case. I mean, you can always... we passed the big boundary, right, because all this is about energy and distance. And until we turned the LHC on, we were either running out of... this idea of these fundamental particles would either be wrong, or we would find the Higgs. Now, we found the Higgs, which means that actually they may carry on being fundamental to very, very high numbers. Whereas if we hadn't found these, and maybe the theories of replacement would be that they're away something else. But I wouldn't want to place bets on whether that really happens. But the standard model is past the Higgs test.
You mentioned the graph.
Yeah.
How can we get that?
Okay, the question was can you detect the graviton? We don't really understand, we don't have a quantum theory of graviton. So you could detect gravitational waves, and there are several experiments looking for that. Some of them very large experiments looking for classical waves, and there was also this whole bicep thing about whether we're seeing signs of gravitational waves in the cosmic magnetic background and so on, which is kind of still out, the jury's out on that, I would say. But the graviton as a quantum particle is more of a postulated thing, because even if we found one, we wouldn't really know how it works. So it'd be great to find out, but we don't have a possibility of graviton. Any more? One more.
Do you have any thoughts on what is it known? Why does the Higgs field, where that comes from?
The question is why does the Higgs field, where that comes from? So we are, now we know there is one, that question has obviously become more front and centre than it was. And one of the weird things about it is, so that what it's this Higgs field is essentially a central energy field, an energy surface. And one of the weird things about it is that we live in this kind of energy minimum, and the universe is a kind of energy minimum. If we weren't in a minimum, it would be this, so it must be an energy minimum. But there might be others, and if there are others, then the universe could suddenly spontaneously move to one of those, which would be bad. There's nothing we can do about it, so I'm not worrying. But it turns out we're right, the masses of the fundamental particles we know of, mostly the top quark and the Higgs boson, except the heaviest ones, tell us we're right on the cusp of this energy surface either having another minimum or not. And we're right at the point where we don't know. And it's like the precision of our measurement might tell us one way or the other. Now, in principle, we could have been anywhere. We knew it had to be stable, but we could have been miles away from this critical point. But we seem to be really close to it. To me, that suggests that we don't fully understand what's going on, because I don't believe in coincidences like that. So, and I think I'm not alone. I think there's a lot of work going on now. That this one number that we measure, there is a Higgs boson, and we measure its mass, so with some precision, is really set a pattern of pigeons about this business of where the Higgs field comes from, what is it really, and this is so. No, this is the hairy age that we don't know. Any more questions? Are there any more questions? It's alright. I can always say no, or I don't know.
I read this video a while ago, and I know it wasn't a very impression of it, but it gave me the impression that the universe is expanding like the universe.
Yeah.
And the impression I got from the book is that the universe needs to be on the surface.
Yeah. Which
made me think, if that's the case, if I travel in that direction long enough, will I go all the way around and come back?
Yeah. So the balloon expanding, so the question was, is the universe like the surface of the balloon on the up one in dimensions? So that's a useful analogy for saying how can it be expanding with no center? Although it's not really, because the balloon has a center, it's another dimension. But it's how you can observe that. Could you go, it depends whether the universe is closed or open. At the moment, it looks like it's open, so that's the flaw that analogy doesn't work. Now, it could have been that the universe was closed, but it's not. The evidence is it's expanding even more quickly. So there are several types of surfaces that will have that behaviour. The one we're familiar with, most familiar with, is the balloon, but there are other kinds of surfaces that are not closed like that. So far, at the moment, we think no, we wouldn't come back to the same place. What is? I'll leave it there. There was something else that was going to go right there, but I forgot what it was. Any more questions? Right, I think that's insatiable.
A couple more questions.
Yeah, I think these are better than the last two, to be honest, because I've got to get a training. Right.
So the power whole thing, have you got dedicated power from a certain place, services?
Yeah. It's not, I mean, okay, it's not it's a significant amount of power, but it's not that big compared to the power you need to run Geneva. Geneva's not very big. It's partly why we shut down in the winter, because when we're running a lot of ski lifts nearby, that's a bit power. So we still do it, but it gets more expensive. So there is, if you go to Spain, you'll see there's a whole bunch of pilots coming in and stopping right there from France. And so there's a significant network in that, but it's not that scale.
Just out of curiosity, if you built the LHC, the straight line, how would it be?
That's a very complicated question. The LHC would have to be very, very long, because to get protons up to that energy, you need an awful lot of power. So the price you pay with protons is, it's hard work bending around the corner, but every time you come past, you just give them another kick. But with a linear one, you only have one shot, so you need a hell of a lot of that. There are proposals for linear electron positron colliders, and that's because the energy limitation on the electrons is not the power, is not the bending around the circle, it's the power you can put in already. Because when they go around the circle, what they do is they radiate the sunlight, just reduce it with a finger. But so there we pretty much reached the crossover point where a linear one-shot thing for electrons is maybe the best way of doing it. But for protons, no way. Okay, that was a lot of good questions. I think I can go get the train now. Thank you all very much.
Thank you very much, John. I refuse personally to believe there's only 17 fundamental particles, because that's a rubbish number. The Cox book on the quantum universe and something or other it's called does happen, yeah, that's the one. There's good explanations on finite diagrams and how that all works that I can understand. I've forgotten now, but that's why if I look into that. Next month we've got philosopher, author and educator Jonathan Pearce coming to talk about free will. This is a topic which I hadn't really considered until I saw his talk last year. I left fascinated and pondering the subject and its implications. So I actually come on to that. This is John questioned him. He's got very interesting concepts that I take on the concept of free will and all the implications that come with it. So thanks all very much for coming. Thanks to Chris, Willow, Simon and Scott. Feel free to hang out in the room afterwards. And we'll see you next time.
Chris, is your brain big enough to understand?